Okay, we'll count. All right, here we go. Binomial distribution. The goal. You guys are going to be able to use binomial distribution to solve probabilities of events, okay? So I kind of hinted at this before, but you can use binomial theorem to basically help you figure out probabilities of events happening multiple times and things like that, okay? So, there are a couple of essential things that you need to know or to check before you determine if this is or is not a binomial distribution type of a problem, okay? Those essential elements being that there are a fixed number of trials, okay? So, if I'm tossing a coin 20 times, 20 is a fixed number, okay? Each trial has only two possible outcomes, a success and a failure. So something like that, like the tossing of the coin, you have one outcome of head, one outcome of tails, okay? So you can only have two possible outcomes. The probability of success is constant from trial to trial, meaning that the probability of flipping a coin is the same whether you flip it the first time, the 12th time, the 19th time. The probability of getting ahead is the same from from experiment to experiment. And lastly, the trials are independent of each other, okay? Meaning that if you flip a coin the first time, it has no effect on the outcome when you flip it the second time. So all these things have to be true in order for it to be a binomial distribution. So, it's a lot. Remember, the video will be posted, so you don't have to write down all this, kind of follow along, write down what you feel is important. The outcome of a binomial experiment and the corresponding probabilities of these outcomes are called a binomial distribution. The binomial distribution describes the behavior of a discrete variable x if the before conditions apply, meaning that those four being fixed, you have two outcomes. The outcomes have the same probability throughout, and that they're independent of each other. A discrete random variable. So these are things that can be counted, such as flipping a coin, rolling a die, grades in a class on a test. Okay, all those things are discrete. It would not work for height. It wouldn't work for weight. It wouldn't work for mass. It wouldn't work for time. Now, the parameters that define a unique binomial distribution are the values of n, the number of trials, and p, the probability of success. Any binomial distribution is represented by this notation here, okay? This notation signifies a binomial distribution, where that capital X, again, represents your discrete variable. The capital B represents a binomial distribution. N, your number of trials, and P, the probability of a success. Let's think about this. Say you want to determine the probability of getting exactly 2 heads in 6 tosses, okay, of a biased coin where the probability of getting a head is 2/3, okay? Now first, let's think about it. Okay, that's 6 tosses, all right, where you could get an outcome of what? What are your 2 outcomes? Heads or tails. And in this particular case of this biased coin, the probability of getting a head is 2/3, okay, which means the probability of getting the tails would be what? 1/3. Now, a tree diagram is out. Because if you think about it, you would have that one branch for the first toss, then 2 branches each for the second toss, then it would be too big. It'd be ridiculous. So, this is a binomial distribution. Does it have all the essential elements met? Are there a fixed number of trials?
Yes.
What's the number? 6. You're tossing a coin 6 times. Are there 2 outcomes?
Yes.
Yes, there are. Heads or tails. Is the one thing. Are they independent? Yes, they are, because, that first toss has nothing to do with the second toss, and then the last one talks about their probability is consistent throughout, right? Whether you toss this biased coin on the first time or on the 5th time, no matter what, isn't head still going to have a 2/3 likelihood of showing up, and the tail's 1/3? Cool, so this is binomial distribution. So to figure this out, what is one possible combination? If you're flipping this coin 6 times, what is an example of one of the outcomes?
All heads.
Heads, and I want 2 heads in 6 tosses. So I can get head, then a head, and then what? Tails, 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 and tails. Okay? So what is the probability of that happening? Okay? Let's figure that out. The probability of getting a head is what? 2/3. So that's 2/3 times 2/3. And then what's the probability of getting a tail? 1/3, 4 times, right? Is everybody following along so far? Now there's another way I can rewrite this, can't I? Instead of doing 2/3 times 2/3 times 1/3 times 1/3. I could write this as 1/3 squared to the 4th and 2/3 to the 2nd. Okay? Let's figure this out. What is that number? 4/9 times 1/81. So what's 4/9 times 181? 4 over. Wow. 729. Jesus. Was 1 times 9 was 8 times 9. 729. So the probability of getting this combination is 4 729s. Now, how many combinations are there to get 2 heads and 4 tails? No, it ain't 729. Combinations. Yeah, now I don't want you to sit up there and list them, but how many combinations? Keyword, where have we seen combinations before? Binomial theorem. Combinations. What would be that top number? 6. So there's 6 total trials, and I want two heads. So that is. Somebody tell me what is 6 combination 2? Forgot the formula, didn't you?
6 times 6 over that.
6 times 5 is 1.
Yeah, that.
6 times 5 times 4 times 3 times 2 times 1 all over.
2 times 1, and then 6 minus 2. Whatever that.
So
15. So to find the probability of getting 2 heads and 6 tosses, you would take those 15 possible combinations and multiply them by the probability of getting 2 heads. And what's 15 times 4? Over 729. And that would be your probability of getting 2 heads and 6 tosses. Okay?
You just multiply 15 times.
The probability of getting 2 heads and 6 tosses.
When you do the square,
Did you do it?
you don't have to add them to how many.
Trials do that? Exactly, because then you'll be missing a trial. So that can all be summed up with the binomial distribution formula. That does deal with combinations, the binomial theorem, which you see on the screen. R represents the successes. So basically what you're trying to find. So in that last example, R represents the number of heads we were trying to get in the 6 tosses. So that's why it was the 2.
The number of successes, right?
And in some shape, way, or form. Yeah. So getting at least 3, getting 1, getting no heads, it would tell you
Like they'll say like the
Success.
number of balls and it's like the red ball.
exactly. But again, it's just a combination times the probability of the success happening times the probability of the failure happening. All right. So here's an example. X binomially distributed with 6 trials and a probability of a success equaling 1/5 at each attempt. What's the probability of exactly 4 successes, 3 or fewer successes, at least 1 success? Okay, so we got 3 different problems that deal with this particular outcome with 6 trials and and a probability of 1/5 of a success. So if it's 1/5 of a success, then this failure is what? 4/5, okay? So the probability that you get exactly 4 successes will look like this. This is how it will be set up. And since this is binomially distributed, we know we're going to use binomial distribution. So I first need my combination. What's the number at the top?
6.
And the number at the bottom?
4.
4. Because I'm looking for 4 successes. So that goes to the bottom. Next, you multiply by the probability of the success happening, which is 1/5. And you raise it to the number of successes that you have, which would be what? 4. Then you multiply it by the probability of the failures happening, which is, and you raise it to the number of,
2.
raise it to the number that won't be, or that the failures will fill.
So would equal to the
Number of trials. Exactly.
like binomial.
Is this the same
Exactly.
thing as what we did before?
Uh-huh. And binomial theorem is to put in with probability, okay? Remember, your exponents have to add up to your top number. And then, of course, your number of successes has to match the exponent of the probability that relates to your successes. And so then, you're good. What's 6 combination 4? Let's use our calculator here. What is 6 combination 4? Huh? It's 15. Times our probability of 1/5 to the 4th, which is 1/5, 6/25, times 8/25. And of course, we're gonna, if we don't put it as a fraction, you always round to what? 3/6. So when we type this in, because this is definitely getting too big for me. Ooh.
40 over 1,565.
Did you do 5 or did you do 15?
No, it's 120.
I did 5.
Okay, so it's gonna be 120 over,
1,565.
Yeah.
so there's your probability of exactly 4.
25. 625.
So there's your probability of exactly 4 successes happening. Probability of 3 or fewer.
Well, it's only at 6.
What do you think we're gonna have to do there?
Do 3 times 2 times 1? Or like,
So it'd be 6.
wait, 3 or 4?
So it'd be 6, 3.
6, 3.
And then
1/5, 3, 4/5, 3.
Okay? So that's your probability of getting 3.
Oh, you can do it separate.
Yeah, I forgot where combinations are.
20. It's 20.
One thousand.
280 over same number 15625.
Okay. Now there's only one problem. That's just the probability of getting 3. You're trying to get 3
Or less.
or fewer. So you have to do the same thing for
2
2,
and 1.
1,
0
and 0.
There's no shortcut for that?
Is there a shortcut? Do you think there might be a shortcut?
Better be a shortcut.
And then some of them are actually just that long. Like you have to do all 3 of them.
I thought maybe you do like,
You have to do for 3, 2,
can you
1,
do the
and 0.
probability of each one and like multiply them? Probability of getting 0, 1, 2, 3. Multiply that.
Can't think of another way, then go ahead. I need 2, I need 1, I need 0, done. I need 2, 1, and 0, done. So you're finishing up the last 4 of the